This is Organic Chemistry 325, Organic Chemistry 1. I want to start by giving you an overview of the chemistry courses that are in this ChemLab technology program. In the third semester we have our first organic chemistry. It's 3 hours lecture and 2 hours lab. We'll be studying infrared spectroscopy and the hydrocarbons alkanes, alkenes, alkynes, and arenes, also called aromatics. It may not sound like much, but there's enough here. And in the course of discussing the preparation and reactions of some of these groups, we'll be introduced to some of the other groups that follow, but we'll cover them in more detail later. Our second organic chemistry course is in the fourth semester, again 3 hours lecture and 2 hours lab. You will learn nuclear magnetic resonance and a host of functional groups: alkyl halides, alcohols and ethers, aldehydes and ketones, the carboxylic acids and the carboxylates, acid anhydrides and acid chlorides, esters, amides, nitriles. The third organic chemistry is in the fifth semester. This is a 3-hour lecture and 3-hour lab. You will learn UV spectroscopy and mass spectroscopy, stereochemistry, molecular orbital theory, amines and amides, and some cycloaddition and substitution reactions. Of all the organics, this is probably the one that requires the most savvy or most understanding. In the sixth semester, you actually have 2 organic chemistries. There's Organic Chemistry 4, 2-hour lecture. This is akin to a biochem course. We'll look at soaps and lipids, carbohydrates, amino acids, and proteins. In fact, this course will become very shortly a 3-hour lecture and a lab. It will basically become a biochemistry course. And also in the sixth semester, we have Polymer Chemistry, 2-hour lecture. So we'll look at mechanisms and methods of polymerization, applications and structures and properties of polymers, industrial processing. So here, this will pull together many of the previous courses and the information related to macromolecules. So organic chemistry, it's vast, it's huge, it's really like an ocean. It's certainly the largest branch of chemistry for its sheer volume of information, and this is the part that is probably most challenging to students. You will need some discipline to practice with repetition because, like mathematics, it builds. You really can't learn fourth semester material if you didn't learn third semester material. It's sequential. So cramming for tests instead of practice really doesn't work well, and students who drop out, it's usually for this reason. Now, at the undergraduate level, conceptually, organic chemistry is one of the simpler chemistries to understand. It's much simpler than, say, physical chemistry or analytical chemistry, even inorganic chemistry, because the millions of different organic chemicals can be reduced to about 18 or 20 different kinds of functional groups. And then the mechanisms by which they react or are prepared, they can be reduced to only a handful. And this is the key to what makes organic chemistry easy. If you strive to understand and practice the mechanisms, the rest will come easy and you will succeed. So let's get started. On the first 2 pages of the CHM 325 notes, you'll find a variety of structures and names of organic compounds. Some of these are complete compounds, some of these are parts of compounds. You'll be required to memorize, to know all of the structures on the first page and on the second page up to and including common nitrogen compounds, down to tertiary amides. The remaining structures, other nitrogen compounds and such, these will be reference material for this first course. So during the first course, we'll be encountering all of these structures, so the sooner you get started to learn them, the better off you'll be. Now, I have a video, it's lecture number 2, that will take you through this piece by piece and help you to learn them. And that's the subject of the second video. But for today, we're going to start on page 3. So what is organic chemistry and what is not organic chemistry? So organic chemistry is the chemistry of carbon-containing compounds as compared to inorganic chemistry, which is the chemistry of non-carbon-containing compounds. What's surprising is if you leave out carbon and consider the other 117 elements, there's only about 500,000 known inorganic compounds. But if you consider carbon and just a few other elements, there's well over 30 million known compounds. And this number increases about 500,000 organic compounds every year. It's staggering how many organic compounds are discovered, newly discovered each year. There's plenty for you yet to discover. This is still not a mature science by any sense. So if we consider carbon, hydrogen, nitrogen, oxygen, the halogens, phosphorus, sulfur, and a few metals, collectively carbon and about 13 different elements give us about 30 million plus known compounds. Of the inorganic compounds, there are some that actually contain carbon but are considered inorganic simply because their properties are more inorganic in nature. For example, diamond and graphite, which are pure carbon, have the behavior of inorganic compounds and are considered inorganic. The ionic carbonates, sodium carbonate, potassium carbonate, lithium carbonate, sodium bicarbonate, calcium carbonate, magnesium carbonate, limestone, inorganic in nature. Also carbonic acid, CO2, carbon monoxide, considered inorganic. And the inorganic cyanides like HCN and KCN. So with these few exceptions, if the compound contains carbon, it's considered to be organic in nature. Now, why is it that carbon and a few other elements can form so many compounds? Well, it's due to the many, many ways in which carbon can bond. Nothing else, no other element is quite like it. So carbon has 4 bonds, or less, and never 5. And you'll be surprised at how many times you or I or other students have written structures that contain 5 bonds and 6 bonds in carbon. Sounds impossible, but it's true. So a prerequisite for learning organic chemistry is that you can count to 4. Now, carbon, recall, is in group 4A. Therefore, it has 4 valence electrons. Now, it's not highly electropositive, neither is it electronegative. Its electronegativity is intermediate, it's 2.5. So it doesn't really like being a cation or an anion, so most of its bonds, most of its compounds involve covalent bonds. Now, being a second period element, it can never have 5 bonds. It can never have more than 8 electrons in the valence shell. So it has available to it 2s2, 2px2, 2py2, and 2pz2 electrons. If we filled all its valence shell, that would be a total of 8 valence electrons, a maximum of 4 bonds, and never more. There are no known compounds of any second period element with more than 8 electrons in the valence shell. They're just not stable. Look at the ways that carbon can bond. So for example, it might have 4 single bonds. These are single bonds. They are also called sigma bonds. Sigma is the Greek letter S, and it's this symbol. So a sigma bond is a bond in which a shared pair of electrons, like the one I'm drawing here, lies between the nuclei of 2 atoms. For example, if this was hydrogen here, then the shared pair of electrons is directly between their nuclei. When carbon forms 4 sigma bonds, or 4 single bonds, we say that it's sp3 hybridized. Now, hybridization is a subject of a previous course, and it will not be taught in this course, but it's important that you know it, so there are some notes reviewing it. You need to review it as necessary that you recall it. So, an sp3 hybridized carbon has bond angles of approximately 110 degrees, which is as far apart as 4 clouds of electrons can get in 3-dimensional space. Let's take a look at a tetrahedral sp3 hybridized carbon. This is methane. Methane has an sp3 hybridized carbon. The bond angles are about 110 degrees. sp3 hybridized. Carbon can also form 2 single bonds and 1 double bond, as you see here. Now the double bond is made of 1 sigma and 1 pi bond. So here's a sigma and a pi. Now this drawing doesn't indicate which one is which. They are different in nature. A pi bond only exists when a sigma bond is already present, whereas the electron density shared between 2 nuclei in a sigma bond is directly between the 2 atoms. The pi bond, which is another pair of electrons, cannot occupy the same space, so it's above and below the plane of the sigma bond. And so a pi bond is not as strong, and furthermore it's weaker. It is somewhat more reactive. It's a reactive site in a compound. And this carbon is sp2 hybridized. The bond angles are 120 degrees. That's as far apart as these bonds can get in 3-dimensional space, and that's described as a flat triangle. We say it's triangular planar. Let's take a look at an sp2 hybridized carbon. So this is ethylene or ethene. It has a carbon-to-carbon double bond. Notice it's a flat triangle in shape, 120 degree bond angles. Each carbon is sp2 hybridized. Carbon can also form bonds 2 sigma and 2 pi bonds, as in the case here, 1 sigma and 1 triple bond, and here we have 2 double bonds. In both of these examples, the carbon is sp hybridized. Let's take a look at such an example. Here's a model of acetylene in which carbon has a single bond and a triple bond. Notice the bond angles are linear, 180 degrees. These carbons are sp hybridized. So our bond angles are 180 degrees, linear molecule. So in these structures, each line represents a covalent bond. It's a shared pair of electrons shared between the 2 atoms. When carbon has 4 bonds, as shown above, then it's neutral. When carbon only has 3 bonds, it exists in one of 3 possible forms. It could be a cation. A cation of carbon is called a carbocation, sometimes called a carbonium ion. It could be an anion, and an anion of carbon is called a carbanion. Or it could be a neutral free radical. So let's look first at a carbocation. Notice it has 3 bonds, 3 sigma bonds, and that's it. It only owns 3 electrons. Being in group 4a, it needs 4 electrons to be neutral, so it's a cation. It has an empty 2pz orbital sitting above and below the carbon here. The carbon is sp2 hybridized. It needs 3 hybridized orbitals to accommodate the 3 pairs of electrons. It has a +1 charge. Almost all carbocations are short-lived species that exist for only fractions of a second in the transition states of chemical reaction intermediates. Now there are a few rare carbocations that can be stabilized. Although most are transitory in nature, their existence is very important in understanding organic reaction mechanisms. Carbanions, on the other hand, are more readily stabilized. That is, we can make some of it, keep it in a jar. It's a charge of -1. Here we have 3 sigma bonds, and then this is not a shared pair, it is a pair that's owned by carbon. Now carbon's not particularly electronegative, and so for it to own a pair of electrons, it must be bonded to something that is very electropositive, like sodium or potassium, and that's exactly where it would occur. This carbon owns 1, 2, 3, 4, 5. It owns 5 electrons, 1 more than the group number, so it is negatively charged. This carbon is sp3 hybridized. It has to accommodate 4 pairs of electrons. A carbanion is the strongest of bases. Its pKb is in the range of -40. That's as strong as they come. And finally we have a carbon free radical. Now notice it has no charge. It owns 1 electron from each covalent bond plus this it owns 4. It is sp2 hybridized. It seems a bit of a conundrum, but I'll go with the consensus in the literature. So apparently this unpaired electron exists in an unhybridized 2pz orbital. It is in fact neutral. Carbon-free radicals are extremely reactive. They don't exist for very long. They'll react with almost anything. So page 4, 5, and 6. I've already mentioned that organic chemistry is this vast ocean. We're going to need a variety of tools. We'll need a toolkit to construct and deconstruct some organic compounds, but before we get started, let's just dip our toe in. Let's get wet and look at some simple hydrocarbons, alkanes, alkenes, and alkynes. So on page 4, alkanes. Alkanes are also called paraffins. Perhaps you've heard the term paraffin wax. Paraffin wax is an alkane of higher molecular weight. It's not a liquid, it's not a gas, but a solid. Now, alkanes are saturated hydrocarbons, and saturated simply means you can't chemically combine any more hydrogen to it. It has no pi bonds, only single bonds. That makes it saturated. The general formula for a saturated hydrocarbon is C to the N, H2N plus 2. So if you know the number of carbons, multiply it by 2 and add 2, and you have the number of hydrogens. Let's look at the first 10 alkanes. We'll start with methane, CH4, and here's its empirical formula. Empirical means experimental. And condensed formula, you'll see the difference between those in just a minute. Next we have the line bond structure. Shows how the carbons and hydrogens are connected. And a skeletal structure, we can't draw that for one carbon. We'll see it next. So let's start then with ethane. That's 2 carbons, therefore the empirical formula would be C2H2N plus 2 is C2H6. The condensed formula looks like this. CH3, that's called a methyl group, bonded to another methyl group. Here's the line bond structure. Now the skeletal structure for ethane looks simply like that. So it's a straight line on an angle. Now the line represents a shared pair of electrons between 2 carbons. The end of each line, or the intersection of each line, represents a carbon with as many hydrogens required to give it 4 bonds. In this case, 3 hydrogens, methyl groups. We draw it on an angle because the bond angles for an sp3 hybridized carbon are about 110 degrees, and we're going to try and simulate that. If you have 3 carbons, that's called propane. That'd be C3H2N plus 2 would be C3H8. The condensed formula is CH3 methyl group. Then CH2, that's called a methylene group, and CH3. So the line bond structure is shown. Here's the skeletal structure. We draw like so. So a line, the first line you draw adds 2 carbons. Every additional line adds 1 more. You can draw it either pointing up or pointing down, the same thing. Here is butane, C4H10. We would draw it as CH3. And then 2 methylene groups. We could draw them separately, or to save space and time, we can put them in parentheses like so. So that's CH3, CH2 taken twice, CH3. Here is the line bond structure. We would draw the skeletal structure as follows. So the first line is 2 carbons. It's 2, 3, 4 carbons. The skeletal structures are by far the easiest way to draw organic molecules. In this course, we'll start mostly with line bond structures. We'll gradually evolve or work our way towards skeletal structures toward the end of the course. Pentane is C5H12. That'd be CH3 with 3 methylene groups. CH2 taken 3 times CH3. We draw it as follows. 2 carbons, 3, 4, and 5. Now I'm going to stop recording here and I'll fill in the rest of the page, and then you can pause the video and fill your own in before we continue. So here I have filled in the remainder of the structures and formulas for the first 10 alkanes: methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, and decane. Many of those prefixes you're probably already familiar with. Perhaps some are new to you. So these alkanes that I've drawn are termed unbranched or straight chain. Now this is the actual shape, if you will. It's hardly straight, but the term is straight chain because if there's a branch, instead of a hydrogen, replace it with a carbon, then that's considered not straight chain. So here we have the saturated hydrocarbons. They will have 4 single bonds. Each carbon is sp3 hybridized. So the molecular geometry is tetrahedral. Each of these carbons is tetrahedral. The bond angles are 110 degrees. Let's take a look next at some alkenes. Alkenes are also called olefins. And alkenes or olefins have one or more pi bond. When you have a pi bond, then you have a double bond. The general formula would be C to the N H2N. So as soon as you have a pi bond, it means that 2 hydrogens have to be removed. So there are 2 hydrogens less in an alkene with 1 double bond as compared to an alkane. The simplest alkene is ethene. That's the IUPAC name. The common name for that is ethylene. And perhaps you've heard the term polyethylene. That's a common name of a polymer made from ethylene. The empirical formula would be C to the N, that's C2, H2N, so that's C2H4. There's the condensed formula. There's the line bond structure. And the skeletal structure is simply a double bond. Looks like an equal sign. If we have a 3-carbon alkene, that'd be C3, H2N, which is H6. So here is the condensed formula for that, the line bond structure, and the skeletal structure would look like this. So the bond angles in an alkene are 120 degrees, and so we show the bent angles between the bonds here. We get to butene, it's 4 carbons, C4H8. Turns out there's actually 3 different isomers, 3 different geometries that can exist in butene. And let's just write the same empirical formula in all cases, C4H8. But look at the differences. This double bond in 1-butene is between the first and second carbon. The number tells the carbon where it first occurs. Numbering whichever direction gives that. I'm numbering left to right in this case. That's 1-butene. Here's the line bond structure. But you can also have the carbon-to-carbon double bond between the second and third carbon in the middle. And that would therefore be called 2-butene, 2 being the number of the carbon to where the double bond first occurs. So if I'm to draw 1-butene in a skeletal structure, I'd have a double bond, and then that's 2, 3, 4. Now, if the carbon-to-carbon double bond is between the second and third carbon, there are still 2 different possibilities. Notice that the carbon in cis-2-butene have hydrogens. They each have 1 hydrogen. Those hydrogens are on the same side of the double bond. Double bonds do not rotate. So there is a side in a carbon-to-carbon double bond. You can be above or below. In this case, both hydrogens are above, and you could say that both methyl groups, CH3 groups, are below. When the hydrogens on the doubly bonded carbons or the methyl groups on the doubly bonded carbons are on the same side, it's called cis, meaning same side. And it would be drawn like this. methyl groups on the same side. If, however, the hydrogens and carbons are on opposite sides, that would be called trans 2-butene. We would draw it in this fashion. And you're probably familiar with the term transatlantic. A transatlantic flight moves across the ocean, so the alkyl groups are on opposite sides of the double bond. And there actually is a word in the English language called cisatlantic, which means on the same side of the Atlantic Ocean, and cis means it has the groups on the same side. So there are actually 3 different isomers of butene. So here are some structures or models. This is ethene, E-N-E, not ane. 120-degree bond angles, triangular planar. Here is cis 2-butene. Here is trans 2-butene. And so a carbon with a double bond has only 3 hybridized orbitals, the 2s, the 2px, and the 2py. And therefore a doubly bonded carbon is sp2 hybridized. The pi bond is formed from an unhybridized 2pz orbital. sp2 hybridized carbon has a triangular planar molecular geometry. It's 120-degree bond angles. Let's next look at alkynes. Alkynes have 1 or more carbon-to-carbon triple bonds. And the general formula is C to the N, H2N minus 2. So recall, for an alkane, it's C to the N, H2N plus 2. If you have an alkene with 1 pi bond, you're going to lose 2 hydrogens, so it's going to be C to the N, H2N. And if you have an alkyne with 1 triple bond, you're going to lose 4 hydrogens, so it's C to the N, H2N minus 2. So the empirical formula for a 2-carbon alkyne, which is called ethyne, or the common name is acetylene, welder's fuel, be C2, H2N minus 2 brings us right back to 2, C2H2. Here is the condensed formula, the line bond structure, and the skeletal structure will simply be a triple bond. So when we draw these skeletal structures, each line represents a bond between 2 carbons. At the end of each line, or the intersection of each line, there is understood to be a carbon with as many hydrogens as required to give carbon 4 bonds. In this case, there'll be 1 hydrogen on each carbon. Propyne, 3 carbons, C3, H2N minus 2, 6 minus 2 is 4, that'd be C3H4. Here's the condensed formula. The line bond structure and the skeletal structure would be a triple bond and a single bond. Now remember that sp hybridized carbons with triple bonds are linear, so this is a straight line, 180-degree bond angles. With butene, again, we have 2 possible structural isomers in which the triple bond could be on the first carbon, that would be 1-butene, or it could be on the second carbon, in which case it's 2-butene. Now there can be no third carbon because if you say this is carbon 3, just flip it around, it's the same if you flip it backwards. In any case, 1-butene has 4 carbons, that's C4H2N minus 2, it looks like 6. There it is. So how do we draw that? Triple bond, and then 2 more carbons, 3 and 4. And finally, 2-butene. This, notice, it does not have geometric isomers because these triply bonded carbons only have 1 group attached, only the methyl groups. So we only have 2-butene, we don't have cis or trans. This also is C4H6. So we draw this as a triple bond with a carbon on each side. So here is a simple alkyne. This is ethyne. A carbon with a triple bond has only 2 hybridized orbitals, the 2s and the 2px. So it's sp hybridized. The 2 pi bonds are formed from unhybridized 2py and 2pz orbitals. An sp hybridized carbon has a linear molecular geometry with 180-degree bond angles. Now there are a list of what I call tools for organic chemistry that you need to master in order to construct and deconstruct organic compounds. Many of these you already know. For example, as simple as Lewis symbols of atoms, electronegativity, polarity, the ability to draw Lewis structures of molecules and assign formal charges to atoms in compounds, and hybridization, and valence bond theory, and VSEPR. And all of this has been covered, and that's for you to review. There's no specific lecture dedicated to it. So in the notes, pages 7 to 19, you'll find a review of all of that material that we've already covered in a previous course, and that's up to you to read and review. And we'll jump in next in our next lecture looking at some new tools that we can use for organic chemistry.